We're going to look now in this video at horizontal rods and moments in regards to horizontal rods and then sitting on supports and the reactions on those supports. Right, first thing, a couple of things. If the question asks you about any assumptions, you're assuming that it's a light beam or considered a light beam, and it would be considered to have no weight. A uniform beam has a weight equally distributed, and the weight acts through the center of the beam. And that really is it. Okay, so have we read through that in your own time there? I'm going to scoot on the questions very quickly. And you can see more assumptions there. Strings and ropes are inextensible, so they don't stretch. Strings and ropes are light, so don't have any weight. And any masses on the rods and beams are considered to be particles. Rods or beams do not bend or flex, and pivots are sharp. So it's not like they're tipping on a rectangular shape or anything like that. Okay, first example, let's get into these quickly. The first example says a light horizontal beam of length 2 meters rests with its ends A and B on smooth supports. The beam carries masses of 5 kilograms and 2 kilograms at a distance of 60 centimeters and 150 centimeters respectively from A. Find the reaction at each. So the whole thing is 2 meters. So let's mark on a few lengths first of all. I'll call this point C. I'll call this point D. And from A to C then is 0.6 meters. A to D was 1.5 meters, so that means that must be 0.9 meters here. And that's 1.5 in total so far, so that must be 0.5 here. I might not need any of all of these lengths, I might. Okay, for the big thing about moments is that there's only 3 things you can do. So you can resolve vertically, resolve horizontally, and you can then take moments about a point. And when I say take moments about a point, I mean you put your clockwise equal to your anti-clockwise. So you're going to see some difficult questions in the next few videos with ladders and hinges and all sorts of things. But remember, if you get into a panic, all the 3 things that all you can do: resolve vertically, resolve horizontally, and take moments about a point. That is it. So we're going to do that in this one. We're going to do the easiest one first, resolve vertically. So I'm just going to make my forces up, which are P and Q, equals my forces down. And the forces down, I've got 5G plus 2G. So I'm just going to say that's P plus Q equals 7G. Okay? And then what I'm doing here, what this means, it means take moments about A, and I'm going to say clockwise equals anti-clockwise. So a moment is a force times its perpendicular distance from the point. So the clockwise ones, I'm going to have this one is going clockwise. So I'll just write it in what it is. That would be 5G times 0.6. I have another clockwise one. This one in this funny blue color would be this one going this way. And it is 2G times 1.5. And then the anti-clockwise one in an horrible orange color here. This one here is going anti-clockwise. So that would have been Q times 2. So bit of working out, that's going to tally up to be 6G equals 2Q, which means Q equals 3G. And then fire that into the first equation then, P plus 3G equals 7G. A wee bit of working out, your Q is equal to 4G. Now, I'll get rid of this so I have a bit of space. You would obviously have to write your answer then. Your answer is going to be, your P is equal to 4 times 9.8, so 39.2 newtons. And your Q is equal to 3 times 9.8, so 29.4 newtons. And that's it done. Okay, the next one. The next one then is a uniform rod AB of mass 40 and length 5 rests on supports at A and C, where AC is 4 meters. Calculate the magnitude of the reaction at each support. No diagram drawn here. And just to show you another way of saying it, there's my A, and there's my B, and where AC is 4. So AC, the whole length of this thing is 5, and AC is 4. So there's my C. So that means that must be 1 meter to this end. If it's 5 meters long, that means my midpoint, and it's uniform, the weight of the thing acts through the midpoint, that's going to be 40 G. And then that's going to be 2.5 meters, not drawn particularly well because that's 1.5 meters here. But there we have it. Okay, and just to show you different, I could have said P and Q. I'm going to call that RA, so the reaction at A and the reaction at B. And we're good to go. Okay, so if we resolve vertical, let me make that a wee bit smaller, made that very big, not haven't left myself any space. So here, if we look at this then, if we resolve vertically, you're going to have RA plus RB is equal to 40G. That's all we've got. And then we're going to take moments. I'm going to take moments about A, and I'm going to use clockwise equals anti-clockwise. And clockwise, this one will be pulling me clockwise. So that's going to be 40G times 2.5 is equal to, and then the anti-clockwise one would be just this one. So anti-clockwise would be, what's that going to be? 2.5 plus 1.5, that's going to be 4. 4 times R, oh, I should have called that R at C, sorry. Call that R at C. 4 times RC, because it was a reaction at C, apologies. And then a wee bit of working out, and I've skipped that out. My RC works out to be 245 newtons. Once you've got your RC, therefore, RA is going to be equal to 40G minus 245, and your reaction at A then works out to be 147 newtons. Okay, so there's that question again in its entirety. Right, firing on to the next one then. Next question says a uniform beam of length 2 meters and mass 4 kilograms has a mass of 3 kilograms attached at one end and a mass of 1 kilogram attached at the other end. Find the position of the support if the beam rests in a horizontal position. So there's only one support. So let's do a decent diagram again here. So there's my A and there's my B. I have 3 kilograms at A. My center is uniform, so 4 kilograms, so 4G. So G, remember, because it's the weight is the mass times acceleration due to gravity. And then your B is only 1G here. And that would be 1 meters because it's only 2 meters long. And then my pivot point is going to be here. And find the position of the support if the beam rests in horizontal. I'm going to call that point C. And I'm going to let this distance here be x, which means this distance from here to here is going to be 1 minus x. Okay. Now there is a force here. I'm even reluctant to put it on. There is some sort of force going up here. We don't really need to find it because what we're going to do is we're going to take moments about the point C, and then we can just do the clockwise equals the anti-clockwise. We don't need to find this force because if we're taking moments about this point, then a force acting through a pivot has no turning effect. The way I like to explain this is if you have somebody on a seesaw, if you've somebody here on a seesaw, the person here on a seesaw, they will have a turning effect. If you've someone right on the edge of a seesaw, they're going to have a turning effect. But if you have someone standing on the pivot, they will not have a turning effect. So this person, they might as well not be here. They don't have any turning effect. So likewise, I'll get rid of this. It might as well not be there. So that's a nice wee way of thinking about it. So if you're on a seesaw, if you're standing on the pivot of a seesaw, you have no turning effect. So what we're going to do here, and by the way, I put my C over here because clearly this thing is heavier on the left than this thing on the right. So if it's going to tip, it's going to tip down on the left. So that support has to be on that side, closer to the 3 kilograms to prevent it tipping that way. So we're going to take moments about C, So we'll just say take moments about C, and again we're doing clockwise equals anti-clockwise. So clockwise, we have two forces. We have this one in yellow, and we have this one in blue. So they're my two clockwise. So I have 4g times 1 minus x, and I have, and this wee distance then would be, here, I forgot to mark it on, it would be 2 minus x is what that distance would be. So I'd have 1g times 2 minus x. And then anti-clockwise, I would just have this one here. So anti-clockwise, I would have 3g times x. Okay? And then we'll multiply that all out. Tidy up is a bit of a mess. 4g minus 4gx plus 2g minus gx is equal to 3gx. I would bring all my g's to the right-hand side. Tidy up the left-hand side. You're going to get 6g. And tidy up the right-hand side, then you're going to get, bring all the other g's, the x's to the other side. You're going to have 3gx plus another gx plus another 4gx. That's going to be 8gx. And then that's going to be 6g. Just write that again. 6g equals 8gx. Cancel out the g's. 6 equals 8x. And then 6 over 8 equals x. My x is 6 over 8, or 3 over 4, or 0.75 meters. And that's it. Okay. 3 more examples to go in this video. Okay, next one. It says a uniform rod AB of length 4 and mass m is resting in a horizontal position on supports C and D, where AC is equal to 0.5 and BD is equal to 1.5. A decent wee diagram again here. So it's AB, length 4, it's uniform, so its weight mass acts to its center. So that's mg newtons acting down. It supports C and D, where AC is only 0.5. So that's 0.5, and that's 1.5 meters. That's my point C. And then whereas BD is 1.5. So that's going to be B to D to here is 1.5. That's 1.5, and that's 0.5. And I'm going to call that reaction at C and reaction at D. Find M and the reaction at D. Does it tell me? It tells me, sorry, the reaction at C is 40. So we'll just call this one, say this one is 40 newtons. So we know this one, happy days. Okay, I like to just do, I'm just going to resolve vertically, see if that gets me anything. It might not. Resolve vertically, I'm going to have 40 plus, that was my reaction at C, which they told me, plus the reaction at D is equal to mg. Hasn't really helped me an awful lot. We'll come back to that. So that is equation 1. And then what I would do here, what on earth did I do here? I'm going to, I think I will take my moments about the D would be the nicest thing. So I'm going to take moments about D. Now this, I probably should have started with this. And again, sometimes you realize as you do a question, you haven't done it the most efficient way. I wouldn't bother scoring it out. I haven't really wasted an awful lot of time. But I would have, if I take moments about D, this force here would actually be going clockwise. So that's my clockwise one. And this force here would be going anti-clockwise. And again, because I'm taking moments about D, I can forget about the reaction at D. So clockwise equals anti-clockwise. The clockwise one I just said was 2 times the 40. And the other one then is the mg times 0.5. Then we'll do a wee bit of working out with that. So 2 times the 40 is 80, and so 80 is equal to 0.5 times the g. So that's 0.5 times 9.8, that's going to be 4.9 m. And then 80 divided by 4.9 is equal to m. M works out to be 16.3265 kilograms. and M is 16.3 kilograms to 3 sig figs. And then we can put that back into equation 1, and you would have then your reaction at D then is equal to the 16.3265 times the M, so times the G, and then minus the 40. And when I did that, worked that out on my calculator, what did I get? I got 120. I got 160 minus the 40. I got my reaction at D to be 120 newtons. Excellent. Okay, 2 more to go. Okay, so these are very similar questions. So I didn't think it was worthwhile doing a separate video for this. These are very similar questions, but this is where instead of being on a pivot, a rod is held suspended by a string. If you have different strings, the assumption you should make is that the tensions in other strings are different. Okay, unless it tells you otherwise. So a uniform rod AB of mass 50. So I'll put that in the middle. And length 4 has a load of mass 25 placed at B. So there's my A, there's my B, and it has at the end of it here, you've got 25 kilograms, 25 G newtons. The rod is held in equilibrium by 2 vertical ropes attached at A. So one's attached at A. So there's a tension, I'm going to call that tension 1. And then the other one at C, where is C? We don't know where C is. Well, given that the tension in the rope at C is 4 times the tension in rope A, find the tension of each. So it's pretty clear to me that my C must be over here somewhere. I'm going to call it tension 2. For this thing to be balanced, it has to be over there. Again, this is a heavier thing, so there's nothing on this end. So to counteract this thing over here, I need to have a tension, something pulling it up this way. So that's why we have got those. So that's why I would put it there. All I can do, resolve vertically, resolve horizontally, find the tension in each rope. Let's just get started. Let's make this a wee bit smaller so we can actually, see this. A bit of space. Okay. Right. We're just going to resolve vertically for part 1. T1 plus T2 is just going to be equal to, what's that going to be? 75G. Haven't been able to do anything with that. We knew something, didn't we? Right. Now, what did it tell you? It told you in the question, given that the tension in the rope at C is 4 times the tension in the rope at A. So we know that T2 is 4 times T1. So we could say then that means T1 plus 4T1 is equal to 75G. So that's 5T1 equals 75G. That means T1 is equal to 15G. All right, so yes, you've worked out the T1. I'd say therefore my T2 is 4 times that. It's going to be 60G, and I'll leave it in terms of G. It'll make life an awful lot easier. So I've actually got both my tensions there. Happy days. Okay, right. The next thing says find the distance CB. So we'll call it X. It's what we're looking for. We're looking for this wee distance. This distance from here to here is 2. And this distance then from here to here would be, the whole thing was 4. So that's going to be 2 minus X. To do this, I would just do, take moments about C is what I would do. We want to find our distance. That's here. It's hard to know which way to do it. I might take moments about A actually, just to show you here. We can do that. So find the distance CB. We'll take moments about A. In actual fact, so we'll take moments about A. So you can do it from any point at all, but I'll take moments about A, and I've got a clockwise force here. I have another clockwise moment here, another clockwise force, another clockwise moment here. And then this one here is going to be our anti-clockwise one. Let me tidy up a wee bit. That's a bit of a mess. This one is going to be our anti-clockwise. Let's just do the anti-clockwise one again. It's going to be this one. Up here is going to be anti-clockwise. So again, just clockwise equals anti-clockwise. So the clockwise, the one in yellow first, that's going to be 50G times 2. The other one is 25G, and it's times 4 because it's that whole length. And anti-clockwise then, it's going to be 2 plus 2 minus x. So the distance is going to be 4 minus x, and it is times our t2. And what was our t2? It was times 60g. Okay, so we'll go with that, and hopefully we get the right thing. So let's just tidy it up. That's going to be 100g plus another 100g. That's going to be 200g on the left-hand side, and then 60 times 4. 60 times 4 is going to be 240g minus 60gx, and then bring that across to the other side. We'll have 60gx is equal to just 40g. Then x is equal to 40g divided by 60g, which is the same as 4 over 6, which is the same as 2 over 3. So my x is 0.667 meters, and that's the 3 sig figs. Okay. That question, you could have done it either way. If why I changed my mind there, I was going to take moments about C. If I'd taken moments about C, this force here that I'm marking in red, and this force here would have had turning effects, but they would have included x. So it just minimized the amount of x's I had in my equation doing it, taking moments about A. But if I'd done it that way, I would have got the right answer. You can try that and see for yourself. Okay, the last part of the question, a very annoying type of question, says state any modeling assumptions. So the ropes are light and inextensible. It would be 1. And another one, we say we treat the masses as particles. Okay, so that's what we've got. And there we are. Okay, our last example for us to do here is a non-uniform rod. So a little bit different. So it says a non-uniform plank, sorry. And non-uniform just means that the mass doesn't act through the center. So it's AB. It has a total length of 10. Rests horizontally in 2 supports, one at A, so we'll mark on my wee support, and one at B. The reactions at A tells you them, happy days, 220 newtons, and at B, it's 280 newtons. Assuming G is equal to 10, let me just highlight that because that's unusual. Assuming G is equal to 10 meters per second squared, and then the center of mass of the plank is X meters from A. So I'm going to guess my center of mass is more over this direction, more to the right, and that's just because my reaction at B is greater. Okay, so that's 10 meters, and that's X meters. That's all we need, and our mass is mg newtons. Do we have to calculate the mass of the plank? Yep, and the value of X. Okay, all we can do, remember, same again, resolve vertically. You're going to have, going downwards, you've got mg, and going upwards, 220 plus 280, sorry, you're going to have 500. And then that is m is equal to 500 divided by g. Remember, g in this question is 10, so m equals 50 kilograms. We worked out the mass of our plank is 50 kilograms already. And then I think the easiest thing to do, take moments about A, clockwise equals anti-clockwise. So clockwise in yellow would be this. So clockwise is going to be my mg, which is now 50g times the x, and anti-clockwise in blue is going to be this, which is going to be 280 times 10. So 50G, so that's going to be 500X equals 2800. Xn is equal to 2800 divided by 500. What's that the same as then? That's going to be just 28 divided by 5, which is just going to be 5.6 meters. And that's it done.